So for the linear independence means what? Means we can construct the linear combination. Okay, linear combination equal, let the linear combination equal 0. And if we find if C1 equals 0, that means linearly independent. Okay, otherwise, if this constant, not all of them equal 0, not all of them equal 0, are linearly dependent. Okay, so from the last class, we did an example and we found these functions are linearly dependent. Okay, so let's take a look at another example. Example 2. F1 x fx, okay, and this guy equals what? Equals equals x minus 1, f2x equals x squared plus x, f3x, for example, equals 3. Now check whether these three equations are linearly independent or not. I'm gonna give you guys 1 or 2 minutes. 2 minutes, okay? Try it by yourself. 2 minutes. Okay, guys, let me write down the answer on board. Okay, So for this type of problem, so first step, you follow the formula, construct the linear combination. All right. So C2, C3 equals 0. Okay. And then what are we gonna get? We plug in C3 times 3 equals 0. Now again, what we can get? We do the distribution. All right, and then combine the terms. For x squared, we have C2x squared. And then we have C1 plus C2x. And C3 minus C1, constant. Right. Then, in order to let all this equation equals 0, that means the coefficient equals 0, right? The coefficient equals 0. That means C2 equals 0, C1 plus C2 equals 0, C3 minus C1 equals 0. Okay. Then C2 equals 0, and we can get what? Because here, 1, 2, 3. If you plug in C2 in this equation, second equation, we're gonna get what? C1 equals 0, right? Because C2 equals 0. And the things C1 equals 0 from the equation 3, that is 0, 2. Okay, is 0, 2. So we can tell C1 equals C2 equals C3 equals 0. Right? That means what? That means these functions are linearly independent. Okay, linearly independent because we found all the coefficients equals 0. Okay, now I'm gonna give you guys another example. Let you guys try it again. Okay, so example 3. Okay, try it again. I give you guys 2 more minutes. Okay. Okay, I'm gonna write down the answer on the board. Okay, it's a very similar to the previous example. What are we gonna do is write down the formula. Okay, write down the formula, and then distribution, right? And then combine the terms. And again, this term. And this term. All right, let me check. So have C2 plus 2. Yes, that's right. And C1 plus C2, C3. Okay, that's right. And in order to let this equation equal 0, that means the coefficient equals 0. C3 minus C1 equals 0. Okay, C3 minus C3. And we have 3 equations. 3 equations. And from the second equation, C2 equals negative C1. For the third equation, we can say C3 equals C1. If we plug in these two to the first equation, what are we gonna get? We're gonna plus in, we're gonna negative C1 plus 2, C3 is C1, okay? And equals 0. I plug in C2 negative C1 here. C3 equals C1 here. And we eliminate C2 and C3, right? And we have only one variable, C1. And you can see this guy equals 0, right? It's a negative C1 equals 0, C1 equals 0. After get C1 equals 0, plugging back, C2 equals 0, C3 equals 0. Okay, so we can see this equation or these functions are linear independent. Linearly independent. Okay, so that's the strategy. That's the strategy. The first step, write down the linear combination and let this guy equals 0. And then do the combination. After you do the combination, you let the coefficient equals 0. And then solve the coefficient C1, C2, C3. If C1, C2, C3 equals 0, that means linearly independent. If some of them are not equal to zeros, that means they are linearly dependent. Okay, linearly independent. Now I'm gonna give you guys the last example. And this one is a little bit tougher. Let's take a look. Number 3. I use the trigger functions. Um, and they help me to linearly dependent or linearly independent on the interval negative pi over 2, pi over 2. Okay. Now, for this guy, you can follow the same steps. I give you guys a little bit of hint. We know that cosine x squared plus sine x squared equals 1. And the secant x squared equals 1 plus tangent x. Okay. So in this processing, you may use these two check relationship. Okay, check relationship. Okay, go ahead, try that by yourself. I gave you guys 2 or 3 minutes. Try it by yourself. After that, I'm gonna give you the answer. Okay, just try it by yourself. Okay, and of course, you may use these two relationship when you try to combine the terms. Okay, combine the terms. Okay, guys, I'm gonna do it on board. It's a little bit tricky in this problems, but you guys need to follow the steps. Okay. So for this guy, we have C1 cosine x squared, C2, C3, C4. Right? As I gave you guys the hints, we know the trig function relationship is here, right? So you probably can use this relationship for the cosine x squared. We let the cosine x squared equals 1 minus sine x squared. So and secant x squared is what? Is 1 plus tangent x squared. Okay. And then you can distribute this term. And what are you gonna get? C1 right? Then we can combine the terms, right? Combine the terms. So for example, we combine the constant C1 plus C3. We combine the sine x is C2 minus C1. Okay. And we can combine the tangent x. Can combine the terms together. Okay, so we got this equation, and definitely we can construct the let the coefficient equals 0, right? Like we did before. Okay, and from the first equation we can get, for example, C3 equals negative C1. And the second equation is C2 equals C1. And then we can plug in this C3 equals negative C1 to this equation, third equation. So plug in negative C1 plus C4 equals 0. That means C4 equals C1, right? As you can see, we can find the equation like that. C2 equals C1, C3 equals negative C1, C4 equals C1, right? We can find the coefficient can be write down as this guy, right? So it's not necessary or equal 0, right? It can be any real numbers for C2, C3, C4, because C1 can be any real numbers. Okay, so if we pick the easiest one, C1 equals 1, then C2 equals 1, C3 equals negative 1. Right? Therefore, we can say we can find the non-zero constants here. Non-zero constants here. That means what? That means these functions are linearly dependent, right? Because they are non-zeros, Okay. So that's the last example, to check the trig functions, whether they are linearly independent or linearly dependent. Okay, and the key part, I think, is the relationship for the trig functions. If you can understand where are these trig function relationship, you plug in and got the solution for the C1, C2, and C3, C4. Okay. Okay, so now let's go to section 4.12. Okay, and today we're going to learn a new terminology, Wronskian, or Wronskian. Let's take a look at the definition for the Wronskian. Definition. 4.12 Wronskian. Suppose each of the function f1, f2, fn possesses sorry, that is at least nth derivative. Derivatives. Derivatives. We can write down the Wronskian is f1 first one is f1, f2. Second one is f1 prime, f2 prime. And the third row, f2 double prime, or f1 double prime, f2 double prime. And the last column gonna be the f1, f2. Oh, sorry, here's n minus 1. Sorry. N minus 1. At least n minus 1 derivatives. Okay, derivatives. So why we need n minus 1 derivatives? Because for Wronskian definition, we need the first row, just copy all the functions, okay? And there's a second row gonna be the derivative of all these functions, derivative functions. And then the second row gonna be the third row gonna be a second derivative. And then the last row gonna be the n minus 1 derivatives. So here it's about n functions, okay? So that means what? That means if I have 3 equations, n equals 3, we just need the first row, second row, third row, right? If we have 3 equations, we just need a third row. Okay, 3 rows. If we have 4 equations, we need 4 rows. Okay, 4 rows. And be careful, if we have 3 equations, we require second derivative. If we have n equals 2, that means we just need first derivative, right? Because n minus 1. N minus 1. So let's take a look. What kind of property we have? Let y1, y2, yn be n solutions of equation 2. Okay, the set of solutions is linearly independent if only if okay. Here the equation 2 means the previously I mentioned the homogeneous equation, nth homogeneous equation. Okay, so nth homogeneous equation, if we can find n solutions, if the Wronskian doesn't equal 0, that means linearly independent. Okay, linearly independent. Previously, now we can use the definition. Now, use the linear combination to find the coefficient, whether the coefficients equal 0 or not. But now we can use much easy way to determine whether a function is linearly independent or not. Linearly independent or not. Okay. For example, we have previous example. Let's take a look. Later I'm going to show you. Okay. So that's the principle. And let's take a look at the other terminologies. Fundamental. Fundamental set of solutions. Any set y1, y2, blah 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 yn of n linearly independent solutions of homogeneous linear nth order differential equation 2 on I is a fundamental set solutions on I. Okay. So what's the meaning of fundamental set of solutions? That means if we have nth order differential equations, we can correspondingly, we have n linearly independent solutions. Then we call the fundamental set of solutions. Okay. So for example, I have second order, for example, okay. For example, I have a second order. I can find these two solutions. Okay, these two solutions. And if we can see these two solutions are linearly independent, okay? These two solutions are linearly independent, then these two solutions corresponding to second order differential equations. This is second differential equations, right? So two solutions, second differential equation. That means this is the fundamental set of solutions. Okay, fundamental set of solution. Y1, Y2 is the form fundamental set of solutions. Okay, set of solutions. Theorem 4.15. General solution. Homogeneous equation. Let Y1, Y2, Yn be a fundamental set of solutions of the homogeneous linear nth order differential equation 2 on I, then the general solution of the equation on the interval is what? It's a linear combination of all of that. Okay, where Ci I equals 1, 2, blah 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 until n are arbitrary constant. Okay, arbitrary constants. So let's take a look. These three terminologies. The first one is Wronskian. Okay, so Wronskian tells us we can use the Wronskian principle to check whether the function is linearly independent or not. Okay, check these functions are linearly independent or not. Okay, so after we find the linearly independent, we check the number. If we find n linearly independent solutions corresponding to nth order, that means this solution form a fundamental set of solutions. Okay, so for example, we have a second differential equations. Correspondingly, we find two linearly independent solutions. That means these two linearly independent solution forms a fundamental set. Okay, fundamental set. And the theorem 4.1.5, if we found the fundamental set, then we can do the linear combination. We can say this guy is the general solution. Okay, this guy is a general solution. So that's the idea. That's the idea. So the first step, we're going to check whether it's linearly independent or not. We're going to use the Wronskian. Okay. And the second step, we're going to check whether the solution forms the fundamental set of solutions. The third step, if it is, then we can say the linear combination of these solutions can be the general solution for the homogeneous differential equation. Okay, so let's take a look at the first example. The functions y1 are both solutions of the homogeneous linear equation on the interval negative infinity infinity. Find the general solution. Okay, now let's follow the steps. The first step, we're gonna calculate the Wronskian. We have two solutions. Wronskian means we have two equations, right? We have two equations. That means we require the first derivative, right? So we just follow these steps. We have the first row is y1, y2, right? So just write down the first row. And the second row gonna be the derivative of the functions, right? Just do the derivative for the first row. Okay, we don't need the third row because we only have two functions, right? Two functions just requires n minus 1. So just the first derivative. Okay, so we just need two functions, two row, two column, right? And how to calculate that this guy? This is a determinant. If you take my linear algebra, you should know how to calculate the determinant, right? Determinant. Or you can, if probably you take the Cal 3, you learned how to do the determinant, right? So just for this guy, just we need to simplify firstly. Okay, we simplify this guy. The derivative of this function gonna be 3e3x because we do the derivative for this composite function 3x. So the value of 3x is going to be 3. And this guy will be -3. Okay. And then we calculate the determinant. Determinant going to be a cross product. And cross subtract the other product. All right. So this guy times this guy, subtract this guy times this guy. So that's the formula. And this guy will give you -3 equals -6. And this guy doesn't equal 0. What does that mean? Based on Wronskian, if Wronskian doesn't equal 0, that means these two solutions are linearly independent, right? So means what? Means are linearly independent. Independent. Okay, third. So here we have two solutions, right? Two solutions corresponding to second order differential equations. Two solutions corresponding to second order differential equations. That means they are forms fundamental set, right? Okay, so since we know there are fundamental set of solutions, then based on the last one, general solution, right? We can find the general solution of the linear combination of these two. We just write down like that. It's the general solution, general solutions. So follow the steps 1, 2, 3, 4. Right? Follow the steps. The first step, check whether they are linearly independent or dependent. Okay, and then check the number of solution and the number of differential equations. And if they are equal, that means they are forms fundamental set of solutions. Okay. Now let me give you guys another one. Let you guys check this guy. And I want you guys try it by yourself. Okay. So follow these steps. Follow these steps. So for example, we have two solutions again. One is e to the power 2x, which is this guy. And they are the solution of corresponding to this guy. Try it by yourself. Okay, try it by yourself. Okay, now, oh, I'll give 1 more minute, okay? 1 more minute. Okay, I'm gonna do it. I'm gonna do it. So the first step, calculate the Wronskian. Copy the second row. Right. And then simplify it. We're gonna get what? The derivative of this guy will be 2, and the derivative of this guy will be a product rule, right? Product rule will be x e to the power 2x plus x 2e to x, right? You do the derivative for the first term, you're gonna get 1. Oh, sorry. Product rule is 1, and then you do the derivative for second term, you're gonna get 2 times e to the power 2x. Okay. Now we can combine the terms. Subtract. Okay. And combine the terms. What do we get? E to the power 4x right? E to the power 4x. And we can say this guy is clearly doesn't equal 0, right? Doesn't equal 0. It's very clearly this guy doesn't equal 0. Right? So that means we can see y1, y2 are linearly independent. Okay. 3, y1 and y2 form a fundamental set of solutions. Okay. 3, 4. Because here, 2 solutions corresponding second order differential equations, right? 2 solutions corresponding second differential equations. So these 2 form a fundamental set of solutions. Then we can do the linear combination of the general solution. Okay, is the general solution. That's it. Follow these 4 steps. Okay, 4 steps. Okay, I'm gonna wrap it up the class here.